Okay, welcome back to our last lecture on Unit 1. We'll pick up next week with Unit 2 and a quiz. So our next quiz is on Tuesday of next week. It's just on 1.4, so it's on partial fraction decomposition. We're going to finish that up today and then spend the rest of the time practicing. And anything we don't get finished with the practice is just more practice to prepare for the exam. I'll make sure that we at least get the answer keys on them, though I don't have, I forgot my notes again at home. I printed them off, but I forgot them. So I don't have the answers, but I will be able to send out the notes after class with the solution guide afterwards. So this was one from 1.3. I don't know if I showed the beginning of it, but basically the thing was by symmetry, we did not need to worry about the bottom half. We could break this up as to two integrals, the integral from 2 to 3 of the square root of 2/3 squared x squared minus 4 plus negative the integral from 2 to 3 of negative 3/2 squared x squared minus 4. But because of symmetry, we can just double it. And then we have to realize that because it has an x squared minus a 4, this is a perfect candidate for a trig substitution. We make x equal to 2 secant theta, which means that dx is equal to 2 secant theta tangent theta. And then I decided to change the bounds. But I guess you could wait till the end to do it if you really wanted to and switch it back in terms of x. But if you're going to change the bounds, when you use x equals 3, you're going to get secant of theta is equal to 3/2. Now, our calculator does not have a button for secant inverse. So you have to realize that secant of theta equaling 3/2, that's the same thing as saying cosine of theta equals 2/3, which means that theta is equal to cosine inverse of that, which is approximately 0.84. Then, now that we've done that trigonometric substitution, we get this 3 times the square root of 4 secant squared root theta minus 4 times 2 secant theta tangent theta. The square root of the inside, that's actually just 2 tangent theta. So we end up with 12 at the end of the day. The integral from 0 to 0.84 of 12 tangent squared theta secant theta. And so there is where the first challenge arises, because that doesn't fit into any of our criteria. There might be a faster way. Here, so that's secant squared. No. You might be able to convert it into sines and cosines and go from there, but it didn't seem to be working out for me when I first tried it that way. Maybe there was a way, but like what you find out in mathematics, I think I've said this to my other classes, but I'm not sure if I've told you guys it. One of my favorite things that I did when I was a grad student is I had a course in mathematics education, and a very, very famous study was showing it was a middle school teacher who was documenting her students who were proficient in mathematics versus her students who weren't. And she gave them a very, very difficult math problem. And the students who were not as proficient, they would try the same technique each time. They would go one direction and then come back to the start and then just keep going back and forwards, like the same thing over and over again. Whereas the students who were proficient, they would try one thing, then they go back to the start, maybe try a different thing, then maybe go back to the start and try the same thing again to get a little bit further, and then go back to the start and then maybe try again and get to the answer. So they were willing to try things and give up halfway through to try a new thing. Maybe they got new information. And so I tried converting the sines and cosines, and it wasn't really working out for me. So what I said was, I got a tangent squared. I can convert that to a secant squared minus 1. Another attempt that I did, and it will work out just differently, is to do integration by parts and split it up as another way to do this one would be to write it so from here, if you make u equal to tangent theta and dv equal to tangent theta secant theta, d theta, that will actually end up working as well. So you can use integration by parts, and it does work out, but I figured it actually ends up being, strangely enough, it ends up being the exact same argument, I think, if memory serves. So this is why at the very beginning it had the note to use a reduction formula, because secant cubed requires a lot of work unless you know the reduction formula. In which case, it reduces down to 1/2 secant theta tangent theta plus natural log of secant theta plus tangent theta. And then we go through the rest of it. The rest of it's basically, after that point, it is a straight plug and chug. Any questions on that one? If anybody would like to take a picture of it, I can get the whole thing up here. If anybody is wanted to, and you can get up and get a bit better view if you'd like. Okay. Does anybody still want to take a picture? Okay. Moving back into 1.4. One thing, it was brought to my attention, and I didn't realize it when we were going through it, and I realize now why so many people were getting confused with me, is I goofed on 1.2.5b. So if we go back to our 1.2 notes, 1.2.5b. So that is not a W on the inside of that cubic. That's a W squared. So it shouldn't FOIL to that. It should FOIL to this. It should go to 3W squared plus W to the 4th plus W to the 6th. So that flips the other things, and then it becomes 1/3 W to the 6th minus W to the 4th plus, no, not W cubed. Sorry, W squared. And then times plus W squared minus 1/3. So these coefficients are wrong, and these exponents are wrong. So let's fix those things. The last one is correct. Yay, I got one part right. So it'll be 1/21 W to the 7th minus 1/5 W to the 5th plus 1/3 W cubed minus 1/3 W. So 1/21 cosine to the 7th over 1/5 W to the 5th and 1/3 cosine to the 3rd. So mistake on my part. Thank you, Victor. Not here, but thank you, Victor, for catching that. That's a silly mistake. Okay? Cool. Anybody still need this up here? I think it's a couple people, yes. Or you can take a picture and do it later. It's your call. Anybody still writing? Okay. And if you need me to go back, just let me know. Onwards and upwards. So, once again, to recap real quick about partial fraction decomposition, I want to go over that over-the-top example to really hammer it home. Any linear factor, any repeated linear factor shows up with each of the powers on it. So that because we have an x cubed in the denominator, that's why we have an a over an x plus a b over x squared plus a c over x cubed. And then any irreducible quadratic factor has an ax plus b numerator. But we have a repeated one with x squared plus 4 squared, so that's why we have ex plus f over x squared plus 4 plus gx plus h over x squared plus 4 squared. So that's the trick. That's the way to do it. And we broke down several of them. And it was all part of the plan so that we could actually just do the integrations without having to worry about it too much. So the integral of negative 2x plus 4 over x squared plus 1 times x minus 1 squared. Now, we had broken that up earlier into that. And this equals, so this equals the integral of 2x plus 1 over x squared plus 1 minus 2 over x minus 1 plus 1 over x minus 1 quantity squared dx. Now, two of those are very quick. And we'll go ahead and write them right beneath it. The 2 over, like this part right here, that's going to be negative 2 ln of absolute value of x minus 1 by our nice nifty integral substitution for natural logs. This third one, the 1 over x minus 1 quantity squared. Now we can go through and do an integral substitution if we really want to, but this actually ends up being negative 1 over x minus 1 to the first power. And the reason for that, and I'll encourage you to check my work. You'll make u equal to x minus 1. So you'll get 1 over u squared, because du will equal dx. And so you get 1 over u squared. The integral of that is u to the negative 1 over negative 1, or negative 1 over u. And that's where we get that piece. Just to save on time. Hope we're okay accepting me at face value, but if you want to see the work, I'm happy to show it. Going once. Absolutely. All right. So if u is equal to x minus 1, then du is equal to dx. So we have the integral of 1 over u squared du, but that's u to the negative 2. So the integral of that would become u to the negative 1 over negative 1, which is negative 1 over u, which is that. Is that okay? All right. Now we're going to take care of the harder one, 2x plus 1 over x squared plus 1. So let's go ahead and do that off on the side, and then we'll write down the final answer at the end. This is why I love color, because it really helps me make sure I separate it into all different pieces, and then those pieces can be combined at the very, very end. So let's go ahead and do that one in blue. Let's make it, I was going to think about doing red at first, but that's going to be a really aggressive. So you have the integral of 2x plus 1 over x squared plus 1 dx. Okay. How should we go about this one? Take a second. Don't say it out loud yet. Get everyone a chance to think about it. How would you do it? Because you could do trigonometric substitution. You could make x equal to tangent theta, but that's actually unnecessary. I mean, you can, and it'll work out. But instead, say we have a better idea, faster idea. Something we forget that we can do is we can split this up into two pieces. We can rewrite this as the integral of 2x over x squared plus 1 over x squared plus 1 dx. And for the record, by the way, if you decided to do trigonometric substitution, it will still work out. So if you don't notice this trick, that's okay. You can still get the right answer. But the reason why I'm doing this, think about why. Think about why. Why would I break it up like this? And I'll give you hints as we, but I want you to ponder it for a second. The reason I did that is this is a nice quick integral. We already know what this is. Tangent inverse. No big deal. And this one, we got an x squared in the denominator and an x to the first power in the numerator. We can do a simple u substitution. So we'll make this just equal to tangent inverse of x. And for this one, let's use orange. We'll make u equal to x squared plus 1, which would give us du is equal to 2x dx. So we have the integral of 1 over u du. Take a second to make sure you agree with my argument here. Normally I do solve for dx with integral substitutions. That's my typical MO. But in this case, since it's already a 2x up in the numerator, I can just immediately swap it with a du. I didn't need to solve for it. And then the integral of 1 over u is natural log of the absolute value of u, which is natural log of x squared plus 1. And I don't need the absolute value anymore because x squared plus 1 is strictly positive. X squared plus 1 is always going to be a number larger than 0, strictly larger than 0. Because x squared is at minimum 0 and at maximum infinity. So you're taking a number that's 0 or larger and adding 1 to it. Now the answer will be 1 or larger. So we don't need the absolute value. I'm not going to mark you down if you put the absolute value, if you do put the absolute value. But I will be a Starbucks barista about it. I will say, like, by the way, it is pronounced caramel macchiato, not macchiato. No, I will have to do that. But anyways, we have everything we need. So let's bring it all together. We've got natural log of x squared plus 1 plus tangent inverse of x minus 2 natural log of the absolute value of x minus 1 minus 1 over x minus 1 plus a constant c. Any questions on that? Okay. Next. Oh, yes, Nick, what's up?
So if we saw this on test, we'd have to do partial fractions first.
Yes. Exactly right. And so we did a bunch of partial fractions to really practice at the beginning, and now we're going to utilize it. And then the last two problems, we are actually going to do the whole thing. So thank you for asking about that. That's good point, because we should get comfortable doing the whole process. But I wanted to make sure we looked at each piece separately, like talking about how to dribble and then also how to shoot. And then we're going to learn how to actually dribble in and get across the court and then do a two-pointer or whatever they call it. I don't know. I'm not a basketball person, but you know the idea. You got to get a goal, right? You got to get a score, which is like basically a touchdown. Yeah. A touchdown at the end zone and a pop fly. Okay, good. So this one, we already broke it down into 2 over 4y squared plus 8y over 4y squared plus 1 squared dy. There's two pieces to them. One of them requires heavier machinery, one of them doesn't. So let's break them down and look at them separately. So I'll call this 1, and I'll call this 2, or you can just bring them, like draw arrows to deal with them. So let's do with 1 right now. The integral, actually, let's use green. Green looks better. Easier to see. The integral of 2 over 4y squared plus 1 dy. What should we do here? Take a second. Make sure everyone gets a chance to think about it, because remember, I'm not going to be there. I mean, I'm going to be here, but I'm not going to be sitting right next to you giving you the answers to the exam. So if this problem shows up, we need to know how to handle it. What do we do? If we do that, I'm glad like that is always the best choice to start off with, is to try and do an integral substitution. But if we make u equal to 4y squared plus 1, then du will equal 8y. But that actually gives us a good idea of what's going to happen here. So it's going to work for the other one, but it's not going to work here, because we'd have a leftover y that we can't get rid of. So what should we do? That looks familiar.
Trig sub.
Trig sub, exactly right. We will make y equal to 1/2 tangent theta, because we want to get the 4 away and get it to be just a 1. So that's why we have the 1/2 there. So that when we square it, the 4 and the 1/4 cancel. If we do that, then dy is equal to 1/2 secant squared theta. So this will equal the integral of 2 over tangent squared theta plus 1 times 1/2 secant squared theta d theta. Any questions on that? There is another option, by the way. There is another way that you could do this without having to do trig sub. You could make u equal to 2y. If you make wait, no. If you make u equal to y over 2, yeah, if you make u equal to y over 2, then you can do a quick integral substitution as well. It will work out that way, but let's get more practice with our trig sub. We need to know how to use it. So anyways, this is secant squared by the trig identity. So, lucky us, the secant squareds immediately cancel. And furthermore, the 2 and the 1/2 cancel. So we end up with the integral of 1 d theta. So that's going to equal just theta. Technically plus c, but we're just going to add a c at the very, very end once we've finished everything. All right. So the only thing left to do is realize that this means that theta is equal to tangent inverse of 2y. Because you'll have tangent of theta equals 2y, so theta is equal to tangent inverse of 2y. So at the end of the day, the first integral piece is tangent inverse of 2y. Any questions on that? On the exam, by the way, you are more than welcome to bring colored pencils, pens, or whatever you'd like to do. If you use colored pens, I would always recommend like we have the technology nowadays where you can actually erase colored pen. There's colored pens that you can erase the ink, which is bonkers to me. But regardless, if you want to, I recommend bringing something that you can like remove the color. My only request is that you reserve red for only minor calculations and things like that. Don't write a whole problem in red because I usually grade in red. So, all right. Then part 2, and it's Savannah, right? Okay. Savannah had correctly suggested u equals 4y squared plus 1. That'll work really nicely here. We'll make u equal to 4y squared plus 1, meaning that du is equal to 8y dy. And normally I would solve for dy. That's the way I usually do integral substitutions, but it's right there for us to grab. The 8y dy is already there to be replaced with a du. So this equals the integral of 1 over u squared du. Is everyone okay with that? Does anybody need to see more work? It's all right if you do. Going once, going twice. Done. And that will equal -1 over u, which is -1 over 4y squared plus 1. So we have everything we need now. We have the green, we have the blue, we'll combine them together. So it's going to be tangent inverse of 2y minus 1 over 4y squared plus 1 plus a constant c. Whew. Okay. Now let's do something for all the marbles. Let's do it all. Win big. Just like the Hawks are going to do this weekend. Am I right? Yeah, we're excited. Fun fact, I did it for my other class. I'm going to do it for you guys. If the Seahawks win, we're dropping another quiz. The Seahawks win the Super Bowl, we're dropping another quiz. We're doing 3 drop quizzes. So you better freaking root for the Seahawks. I'm getting my son a Lego to play during the game, as is tradition. So that because he doesn't really like football yet. So his loss. Okay. So the next one, this is for all the marbles. This is these two right here. We need to know how to work through these. So one thing I will tell you off the bat, because you guys are gonna go through this one. X squared plus x plus 1 is an irreducible quadratic. If you try and do b squared minus 4ac, you get 1 minus 4, and that's a negative number. So that thing has complex roots. So we need to partially fraction break it down and then integrate the result. So I want you to go ahead and start working through this one. I will slowly fill in details. And people watching the recording, so you should pause it too. And if you get stumped, I'll be slowly updating it as we go along.